We will cover AI in healthcare, AI in financial services, and AI in autonomous vehicles. By the end of this unit, you'll be able to list examples of the impact of AI across different industries, describe how AI is revolutionizing drug discovery and medical devices, articulate examples of how AI is transforming industries in the financial sector, illustrate how automakers are using AI from design to self-driving cars. Let's get started.
I am a translator, transforming text into creative discovery. Movement into animation, and direction into action. I am a healer, exploring the building blocks that make us unique. Modeling new threats before they happen. And searching for the cures to keep them at bay. I am a visionary, generating new medical miracles. And giving us a new perspective on our sun to keep us safe here on Earth. I am a navigator, discovering a unique moment in a sea of content.
We're announcing the next generation.
And the perfect setting for any story. I am a creator, building 3D experiences from into our virtual selves. I am a helper, bringing brainstorms to life.
Maybe learn from different angles.
Sharing the wisdom of a million programmers, and turning ideas into virtual worlds.
Build northern forest.
I even helped write the script. Breathed life into the words and composed the melody. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
A quote from Jensen Huang, the CEO of NVIDIA. We are leveraging the capabilities of AI to perform intuitive tasks on a scale that is quite hard to imagine, and no industry can afford to or wants to miss out on the huge advantages that predictive analytics offers. AI has the transformative potential to infuse every industry due to its capacity to enhance efficiency, decision-making, and innovation. By leveraging advanced algorithms, machine learning, and data analytics, AI can streamline processes, automate tasks, and uncover valuable insights from vast data sets. To name a few examples, in call centers, AI can advance and accelerate many applications such as AI virtual agents, insight extraction, and sentiment analysis. In retail, AI can be used to provide insights for store analytics, such as store traffic trends, counts of customers with shopping baskets, aisle occupancy, and more. In manufacturing, AI can help design products, optimize production, improve quality control, reduce waste, and increase safety. AI has seamlessly woven itself into the fabric of our daily lives, leaving an indelible impact on how we work, communicate, and navigate the world. Many familiar technologies found in our day-to-day lives are powered by AI, and many more are being added to an ever-evolving landscape of possibilities. The computer industry is currently undergoing transformative shifts that are reshaping the technological landscape. One notable trend is the explosion of generative AI, which is pushing the boundaries of artificial intelligence applications. Generative AI models are demonstrating unprecedented capabilities in natural language processing, content creation, and problem solving, integrating diverse data sources to create rich and contextually relevant outputs across various sensory modalities, such as text, images, and sound. We'll discuss generative AI in greater detail in the third unit of this course. For now, let's shift our focus to our first industry, the healthcare sector. Let's see some real-world examples of AI in healthcare. The drug discovery process has traditionally been expensive, long, and laborious. It is a $1.2 trillion industry with approximately $2 billion research and development investment per drug. These drugs normally go through more than 10 years of development and have a 90% failure rate. By providing rich and diverse data sets that can be leveraged to train and validate AI models, AI is revolutionizing drug discovery by significantly impacting various stages of the drug development process. Digital biology can be used to identify new drug targets, predict the efficacy and toxicity of drug candidates, and optimize the design of new drugs. By using computational methods to model the interactions between drugs and biological systems, researchers can accelerate the drug discovery process and reduce the costs associated with traditional drug development. Lab automation, which is generating vast amounts of data in drug discovery, and the ability to process and analyze this data is becoming increasingly important for drug development. Advanced data analytics and machine learning techniques are being developed to help make sense of this data and accelerate the drug discovery process. AI and computing are revolutionizing drug discovery by enabling researchers to analyze and understand large amounts of data, develop more accurate models, and identify promising new drug candidates more quickly and efficiently. Medical devices are going through a revolution right now, where sensor information is augmented with software, advanced computing, and AI to do amazing things. Nowadays, medical devices can utilize continuous sensing, computation, and AI to detect, measure, predict, and guide high-risk precision medical operations. This evolution suggests that the healthcare sector is heading towards a more robotic approach, augmenting clinical care teams to meet demand, maximize efficiency, and enhance access to care. Invenio Imaging is a medical device company developing technology that enables surgeons to evaluate tissue biopsies in the operating room immediately after samples are collected, providing in just 3 minutes AI-accelerated insights that would otherwise take weeks to obtain from a pathology lab. Invenio uses a cluster of NVIDIA RTX GPUs to train AI neural networks with tens of millions of parameters on pathologist-annotated images. These models are layered on top of images, providing real-time image analysis and allowing physicians to quickly determine what kinds of cancer cells are present in a biopsy image. With the ability to analyze different molecular subtypes of cancer within a tissue sample, doctors can predict how well a patient will respond to chemotherapy or determine whether a tumor has been successfully removed during surgery. Next, we'll talk about how AI affects financial services. One of AI's incredible breakthroughs is the ability to identify patterns hidden in vast amounts of data at levels of precision, speed, and scale that were previously impossible to reach. This ability brings multiple benefits to the financial services industry, from enabling more intelligent trading to expanding credit and services to underserved people. Let's view a couple of different examples of how large financial institutions are leveraging AI to reduce fraud and improve customer experience. Our first example is the Frankfurt-based Deutsche Bank, a leading global investment bank, is working with NVIDIA to accelerate the use of AI and machine learning on transformational AI applications. With NVIDIA's Omniverse platform, an open computing platform for building and operating metaverse applications, Deutsche Bank is exploring how to engage with employees and customers more interactively, improving experiences using 3D virtual avatars to help employees navigate internal systems and respond to HR-related questions. Deutsche Bank and NVIDIA are testing a collection of large language models targeted at financial data called financial transformers, or finformers. These systems will achieve outcomes such as early warning signs on the counterparty of a financial transaction, faster data retrieval, and identifying data quality issues. The second example is American Express. Credit and bank cards are a major target for fraud. To thwart fraudulent activity, American Express, which handles more than 8 billion transactions a year, leverages deep learning through the NVIDIA GPU computing platform. Using advanced AI models to detect anomalous patterns in transactions, American Express implemented an enhanced real-time fraud detection system to improve accuracy and better protect its customers and merchants, while operating within a tight 2-millisecond latency requirement. Let's move on to our final sector. Let's learn how AI is being used in autonomous vehicles. The impact of artificial intelligence in the automotive industry has been transformative, revolutionizing the way vehicles are designed, manufactured, and operated. Let's look at a few examples that illustrate this transformation. Design visualization. Photorealistic rendering empowers designers to take advantage of immersive, real-time, physically accurate visualizations. Engineering simulation. Engineers and simulation experts can rapidly analyze and solve complex problems with GPU-accelerated hardware and software tools. Industrial digital twin. With NVIDIA Omniverse Enterprise, automakers can quickly develop and operate complex AI-enabled digital twins, maximize productivity, and help maintain faultless operation. Virtual showrooms and car configurators. As the buying experience migrates from physical retail spaces to online, dealerships can offer photoreal interactive content for personal experiences. Intelligent assistants. With conversational AI, natural language understanding, and recommendation engines, intelligent in-vehicle services can act as every passenger's digital assistant. autonomous driving and parking. Autonomous vehicles are transforming the way we live, work, and play, creating safer and more efficient roads. These revolutionary benefits require massive computational horsepower and large-scale production software expertise. Tapping into decades-long experience in high-performance computing, imaging, and AI, NVIDIA has built a software-defined end-to-end platform for the transportation industry that enables continuous improvement and deployment through over-the-air updates.
Welcome, Daniel. I see a text from Hubert asking, can you pick me up from the San Jose Civic? Should I take you there?
Yes, please.
Okay, taking you to San Jose Civic.
Start Drive Pilot.
Okay, starting Drive Pilot.
Can you let Hubert know we're on our way?
Sure, I'll send him a text.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast, I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last, yeah. Now that I've been put through hell, I never got anyone's help. I had to do it all myself. I don't ever slow up, no I don't take shit.
You have arrived at your destination.
Please park the vehicle.
Okay, finding a parking spot.
Vehicle production is a colossal undertaking requiring thousands of parts and workers moving in harmony. Any supply chain or production issues can lead to costly delays. Additionally, when automakers roll out a new model, they must reconfigure the layout of production plants to account for the new vehicle design. This process can take significant portions of the factory offline, pausing manufacturing for existing vehicles. Mercedes-Benz is digitizing its production process using the NVIDIA Omniverse platform to design and plan manufacturing and assembly facilities. NVIDIA Omniverse is an open 3D development platform enabling enterprises and institutions across all industries to build and operate digital twins for industrial and scientific use cases. By tapping into NVIDIA AI and metaverse technologies, the automaker can create feedback loops to reduce waste, decrease energy consumption, and continuously enhance quality.
NVIDIA Omniverse is a scalable, end-to-end platform enabling all industries to build and operate digital twins for scientific research, infrastructure, product design, architecture, and more. Now, Mercedes-Benz is using Omniverse to optimize new production and assembly facilities. Building a car requires thousands of parts and workers all moving in harmony. Using digital twins created in Omniverse, an assembly line for a new model can be reconfigured in simulation without interrupting current production. Production planners can synchronize plants around the world, enabling over-the-air software updates to manufacturing equipment, streamlining operations while improving quality and efficiency. Mercedes-Benz is preparing to manufacture its new EV platform at its plant in Rastatt, Germany. Operations experts are simulating new production processes in Omniverse, which can be used alongside existing vehicle production. This virtual workflow also allows the automaker to quickly react to supply chain disruptions, reconfiguring the assembly line as needed. Using NVIDIA AI and Omniverse, Mercedes-Benz is building intelligent, sustainable factories that improve efficiency, reduce waste, and continually enhance vehicle quality.
AI is powering change in every industry. From speech recognition and recommenders to medical imaging and improved supply chain management, AI is providing enterprises the compute power, tools, and algorithms their teams need to do their life's work. From the cloud, to the office, to the data center, to the edge, AI-powered solutions revolutionize enterprise operations by enhancing efficiency, automating complex tasks, optimizing decision-making processes, and unlocking valuable insights from vast datasets. Welcome to the Introduction to Artificial Intelligence unit. Today, we'll delve into the foundations of AI. We'll unravel the basics and provide you with a solid understanding of artificial intelligence, laying the groundwork for your journey into this exciting field. In this unit, we cover an introduction to AI and its evolution through the years, typical steps of an AI workflow, a brief explanation of how deep learning works, ML and DL features and comparison, and challenges when deploying AI in production. By the end of this unit, you'll be able to describe key milestones in the evolution of AI, visualize a typical AI workflow and the main steps in each phase, describe in high level how neural networks work, identify common challenges enterprises face when adopting AI, and articulate the value of NVIDIA end-to-end software stack for deploying AI solutions in production. Let's get started. AI is a broad field of study focused on using computers to do things that require human-level intelligence. It has been around since the 1950s, used in games like tic-tac-toe and checkers, and inspiring scary sci-fi movies, but it was limited in practical applications. Machine learning, or ML, came in the 80s as an approach to AI that uses statistics techniques to construct a model from observed data. It generally relies on human-defined classifiers, or feature extractors, that can be as simple as a linear regression, or the slightly more complicated bag of words analysis technique that made email spam filters possible. This was very handy in the late 1980s when email spam started becoming an issue for many users. With the invention of smartphones, webcams, and social media services, and all kinds of sensors that generate huge mountains of data, a new challenge presented itself, that of understanding and extracting insights from all this big data. Real breakthroughs with deep learning, or DL, came around 2010, largely due to advances in hardware, the availability of large data sets, and improvements in training algorithms, which automated the creation of feature extractors using large amounts of data to train complex deep neural networks, or DNNs. Within only 1 decade from the advancements brought by DNNs, we are now in a new era of generative AI and large language models with systems that are surprisingly human-like in their intelligence and capabilities. Applications such as chatbots, virtual assistants, content generation, translation services, and more are impacting industries and our daily lives. We will continue the discussion on generative AI in the next unit. An AI workflow, often referred to as a machine learning workflow or data science workflow, is a sequence of tasks and processes that data scientists, machine learning engineers, and AI practitioners follow to develop, train, deploy, and maintain artificial intelligence models. These workflows help to ensure that AI projects are systematic, well-documented, and effective. Let's consider a typical AI workflow broken down into 4 fundamental steps. The first step is data preparation, which involves collecting, cleaning, and pre-processing raw data to make it suitable for training and evaluating artificial intelligence models. The size of a dataset used in model training can vary from small to very large datasets with billions of parameters. Ultimately, the quality, diversity, and relevance of the data are as important as the dataset size. Once the data has been prepared accordingly, it is fed into a model. The model training step of an AI workflow involves using a machine learning or deep learning model to learn patterns and relationships within a labeled dataset. The model is trained over a set of data by using a mathematical algorithm to process and learn from the data. This is a critical part of the AI workflow. It involves teaching the AI model to recognize patterns and make predictions. Data scientists can iterate many times before producing a model that's ready for deployment. The training step is the most compute-intensive phase of the AI workflow, usually benefiting the most from more hardware than the other steps, including inference. To make the training step more efficient while maintaining model accuracy, training is usually done with mixed precision data formats, such as FP8 or FP16, among others. Model optimization is a crucial step in an AI workflow. It involves fine-tuning and enhancing the performance of the AI model to make it more accurate, efficient, and suitable for its intended use case. It's an iterative process where adjustments are made based on evaluation results, and the model is fine-tuned until it meets the desired performance criteria for deployment. Once you've trained the model, it's ready to deploy into inference. It involves using a trained machine learning or deep learning model to make predictions, decisions, or generate outputs based on new, unseen data. This step typically occurs after the model has been trained and validated and is ready to be deployed in a real-world or production environment. Inference is often the core of AI applications, where the model's ability to provide meaningful and accurate outputs is essential for addressing real-world challenges and achieving the application's objectives. Let's see a typical AI workflow example for deploying an image recognition solution alongside the tools that can be used in each step. ImageMe is a radiology clinic that provides services such as MRIs, X-rays, and CT scans to several doctor offices. They want to enhance their services by adding image recognition of fractures and tumors, helping doctors and their diagnostics. Sarah, an ML engineer, gathers historical datasets containing X-rays, CT scans, and MRIs from hospital, research institutes, and their own inventory. For the data preparation step, she uses Rapids, an open-source suite of GPU-accelerated Python libraries built on NVIDIA AI to perform analytics and to prepare data for machine learning. She leverages the Rapids accelerator for Apache Spark, a plugin software that automatically intercepts and accelerates operations that can be sped up with Rapids software and GPUs while allowing other operations to continue running on the CPU. Once the data prep is complete, PyTorch and TensorFlow are the GPU-accelerated computational frameworks that can be used to train the model at scale. They are now integrated with NVIDIA Rapids to simplify enterprise AI development. Once the model training is complete, it can be optimized using NVIDIA TensorRT, a deep learning inference optimizer to fine-tune and improve the model's performance, making it ready to be deployed, executed, and scaled. Lastly, AI inference applies logical rules to the knowledge base to evaluate and analyze new information. She uses NVIDIA Triton Inference Server as an open-source software that standardizes AI model deployment, execution, and takes care of all IT and DevOps deployment aspects, such as load balancing. We've discussed typical AI workflow steps and provided an example. Now, let's shift our attention to the intricacies of deep learning. Geoffrey Hinton, the godfather of deep learning and AI, once said, "I've always been convinced that the only way to get artificial intelligence to work is to do the computation in a way similar to the human brain. That is the goal I have been pursuing. We are making progress, though we still have lots to learn about how the brain actually works." Let's get a better understanding of what exactly Geoffrey meant. Earlier, we mentioned that deep learning harnesses deep neural networks, or DNNs, to achieve levels of accuracy that rival human capabilities. But have you ever wondered how these neural networks in AI are inspired by the human brain? Well, it all begins with a bit of neuroscience. Let's compare the works of a biological neuron to an artificial neuron. Artificial neural networks take a page from the human brain's playbook. Picture this. In our brain, there are tiny components called neurons. Neurons are like tiny information messengers. They communicate through a series of events. First, dendrites, which act as the receiving antennas of neurons, pick up signals from neighboring neurons' terminal buttons. These signals are then sent to the cell nucleus for some processing magic. After that, the electrical impulse zips along a longer branch called the axon, making its way to the synapse. The synapse acts as a bridge, passing the impulse to the dendrites of another neuron. It's like a relay race of information, creating a complex neural network in the human brain. As you can tell from the on-screen animation, artificial neurons are fundamentally inspired by the workings of biological neurons. So, what is the deep learning workflow? Consider an application that automatically identifies various types of animals, in other words, a classification task. The first step is to assemble a collection of representative examples to be used as a training dataset, which will serve as the experience from which a neural network will learn. As we just learned, neural networks are algorithms that draw inspiration from the human brain in understanding complex patterns. If the classification is only cats versus dogs, then only cat and dog images are needed in the training dataset. In this case, several thousand images will be needed, each with a label indicating whether it is a cat image or a dog image. To ensure the training dataset is representative of all the pictures of cats and dogs that exist in the world, it must include a wide range of species, poses, and environments in which dogs and cats may be observed. The next component that is needed is a deep neural network model. Typically, this will be an untrained neural network designed to perform a general task like detection, classification, or segmentation on a specific type of input data like images, text, audio, or video. Shown here is a simple model of an untrained neural network. At the top of the model, there is a row or layer that has 5 input nodes, and at the bottom there is a layer that has 2 output nodes. Between the input layer and the output layer are a few hidden layers with several nodes each. The interconnecting lines show which nodes in the input layer share their results with nodes in the first hidden layer, and so on, all the way down to the output layer. Nodes may be referenced as artificial neurons or perceptrons, since their simple behavior is inspired by the neurons in the human brain. A typical deep neural network model would have many hidden layers between the input layer and the output layer, which is why it is called deep. We use a simplified representation on this slide for brevity. The design of the neural network model is what makes it suitable for a particular task. For example, image classification models are very different from speech recognition models. The differences can include the number of layers, the number of nodes in each layer, the algorithms performed in each node, and the connections between the nodes. There are readily available deep neural network models for image classification, object recognition, image segmentation, and several other tasks, but it is often necessary to modify these models to achieve high levels of accuracy for a particular dataset. For the image classification task to distinguish images of cats versus dogs, a convolutional neural network, such as AlexNet, would probably be used. AlexNet is comprised of nodes that implement simple generalized algorithms. Using these simple generalized algorithms is a key difference and advantage for deep learning versus earlier approaches to machine learning, which required many custom data-specific feature extraction algorithms to be developed by specialists for each dataset and task. Once a training dataset has been assembled and a neural network model selected, a deep learning framework is used to feed the training dataset through the neural network. For each image that is processed through the neural network, each node in the output layer reports a number that indicates how confident it is that the image is a dog or a cat. In this case, there are only two options, so the model needs just two nodes in the output layer, one for dogs and one for cats. When these final outputs are sorted in a most confident to least confident manner, the result is called a confidence vector. The deep learning framework then looks at the label for the image to determine whether the neural network guessed or inferred the correct answer. If it inferred correctly, the framework strengthened the weights of the connections that contributed to getting the correct answer. And vice versa. If the neural network inferred the incorrect result, the framework reduces the weights of the connections that contributed to getting the wrong answer. After processing the entire training dataset once, the neural network will generally have enough experience to infer the correct answer a little more than half of the time, slightly better than a random coin toss. It'll require several additional rounds to achieve higher levels of accuracy. Now that the model has been trained on a large representative dataset, it has become better at distinguishing between cats and dogs. But if it were shown a picture of a raccoon, it would likely assign comparable confidence scores to both the dog and cat, as it wouldn't be certain about identifying either one. If it was necessary to classify raccoons as well as dogs and cats, the design topology of the model would need to be modified to add a third node to the output layer. The training data set would be expanded to include thousands of representative images of raccoons and use the deep learning framework to retrain the model. Once the model has been trained, much of the generalized flexibility that was necessary during the training process is no longer needed, so it is possible to optimize the model for significantly faster runtime performance. Common optimizations include fusing layers to reduce memory and communication overhead, pruning nodes that do not contribute significantly to the results, and other techniques. The fully trained and optimized model is then ready to be integrated into an application that will feed it new data, in this case, images of cats and dogs that it hasn't seen before. As a result, it will be able to quickly and accurately infer the correct answer based on its training. Let's summarize the key differences in the realm of AI we've covered till now. When most technology companies talk about doing AI, they're talking about using machines to mimic human abilities to learn, analyze, and predict. Machine learning achieves that by using large data sets and sophisticated statistical methods to train a model to predict outcomes from new incoming information. One of the most popular machine learning techniques used these days is deep learning. Deep learning uses artificial neural networks to learn from vast amounts of data to solve AI problems, and really shines for use cases involving vision and speech. Generative AI is a type of artificial intelligence that uses machine learning algorithms to learn patterns and trends from the training data using neural networks to create new content that mimics human-generated content. Now that we've gained a deeper understanding of AI and the intricacies of deep learning workflows, let's turn our attention to the individuals and organizations who are actively employing AI. We'll also explore the challenges they encounter while trying to harness the capabilities of AI. In an AI data center, various stakeholders play crucial roles in the planning, development, and operation of AI infrastructure and applications. AI practitioners create applications that extract meaningful data from large data sets using machine learning. They desire an agile, cloud-native platform that can quickly evolve to support the latest in AI, with accuracy and performance that can accelerate time to deployment. For enterprise IT, who manages the company's infrastructure, data, and application lifecycle, AI is still an emerging workload and rapidly evolving. Managing rapidly changing applications and often open-source platforms and tools can be a challenge for an IT department that is most likely also dealing with older infrastructure and technical debt, for example. They want to ensure the data center's infrastructure meets AI workloads demands with an optimized platform to bring AI into production. Line of business managers want to see more models deployed in production sooner by ensuring the efficient utilization of the investments in infrastructure and platforms. Leaders are constantly looking for the quickest way to excel return on investment and provide data-driven results from their investment in AI infrastructure. The benefits of AI are massive, but fully realizing those benefits requires a comprehensive solution. Along with many of these benefits come certain challenges which are essential to consider when adopting AI. Exploding model sizes and complexity. State-of-the-art AI models continue to rapidly evolve and expand in size, complexity, and diversity. The rapid growth of AI models demands extensive computational resources and energy, potentially limiting affordability and sustainability and posing accessibility challenges for smaller organizations. The versatility required to deliver rich experience. AI-enabled applications like product recommendations, voice assistance, and contact center automation may require multiple different powerful models to be deployed within the same application in order to deliver a fantastic user experience. Performance and scalability. Training these AI models and customizing them for your unique application is an intense, complex, iterative process. End-to-end performance, considering both the individual steps and each overall iteration, is critical for accelerating toward a solution. Taking AI to production requires tools to support the end-to-end AI lifecycle, compute infrastructure, and a robust support model to ensure all key stakeholders, the data scientists, engineers, developers, and operators, are able to meet their unique goals. NVIDIA contributes to addressing these challenges by providing AI practitioners with top-tier development tools, frameworks, and pre-trained models. Additionally, the platform offers reliable management and orchestration solutions for IT professionals, guaranteeing performance, high availability, and security. The NVIDIA AI software stack enables the full AI pipeline from data prep for model training through inferencing and ultimately scaling. It accelerates time to production with AI workflows and pre-trained models for specific business outcomes, such as intelligent virtual assistants, digital fingerprinting for real-time cybersecurity threat detection, and recommender systems for online retail to help understand consumer behaviors and increase customer engagement. Finally, your AI solution is optimized and certified to deploy everywhere, from public cloud to data centers to the edge devices. This provides the flexibility and reduces the risk of moving from pilot to production caused by infrastructure and architectural differences between environments. Well done for making it to the end of this unit. Now you should be able to describe key milestones in the evolution of AI, visualize a typical AI workflow and the main steps in each phase, describe in high level how neural networks work, identify common challenges enterprises face when adopting AI, articulate value of NVIDIA end-to-end software stack for deploying AI solutions in production. Welcome. This is the third unit in the course, which covers an overview of generative AI. Here's the outline for this unit. Unit 3 is aimed at understanding what generative AI is, how the technology works, an overview of large language models, or LLMs, and the steps required to deploy generative AI solutions in the enterprise. By the end of this unit, you'll be able to explain what generative AI is and how the technology works, discuss at a high level the main concepts of large language models, and describe the steps required for enterprises to unlock new opportunities for their business. In the previous unit, we learned about the AI process that allows us to reach generative AI, but let's get a better understanding of exactly what it is. Generative AI refers to a subset of artificial intelligence that focuses on creating data or content, such as images, text, and multimedia, based on patterns and examples from a given dataset. What sets generative AI apart is its versatility, enabling it to perform a wide array of tasks beyond text and chat-based applications. These systems can generate diverse forms of content, including realistic images, videos, music, and even entire virtual environments, by learning from and synthesizing patterns in the input data. Its adaptability to diverse data types and applications underscores its potential to transform multiple industries and augment human capabilities across a wide spectrum of tasks. Generative AI is making inroads into every industry, transforming traditional practices and bringing forth unprecedented operational efficiency and innovation. In finance, it enhances fraud detection, personalized banking, and provides valuable investment insights. Within healthcare, it powers molecule simulation, drug discovery, and clinical trial data analysis. Retail benefits from personalized shopping, automated catalog descriptions, and automatic price optimization. In manufacturing, it transforms factory simulation, product design, and predictive maintenance. These are just some examples of the innovations brought by generative AI. Foundational models serve as the basis or foundation for the creation and evolution of generative AI systems, providing the initial framework for understanding complex language structures, semantics, and contextual nuances. They consist of AI neural networks trained on massive unlabeled datasets to handle a wide variety of jobs, such as generating text, images, summarizing documents, translating languages, and more. One of the breakthroughs with generative AI models is the ability to leverage different learning approaches, including unsupervised or semi-supervised learning for training. That is, it relies on finding patterns and structures in the data on its own without requiring labeled data to train a model. DALL-E creates realistic images from text descriptions. It can be used for image synthesis tasks such as image captioning, image editing, or image manipulation. Edify is a diffusion model for synthesizing images given text which generate photorealistic images corresponding to any input text prompt. Llama 2 can be used for generating diverse and high-quality natural language text, making it valuable for various tasks such as content creation, language understanding, and conversational AI applications. NVIDIA GPT is a family of production-ready large language models, or LLMs, that can be tuned to build enterprise generative AI applications that can perform a range of tasks, from creating product descriptions, answering customer queries, and writing code. GPT-4 gives applications the ability to create human-like text and content, images, music, and more, and answer questions in a conversational manner. We just saw examples of foundation models. Let's now discuss how they are trained. The large language models, or LLMs, powering the advances in generative AI are a significant turning point. They've not only cracked the code on language complexity, enabling machines to learn context, infer intent, and be independently creative, but they can also be fine-tuned for a wide range of different tasks. A foundation model is trained on a large amount of unlabeled data, that is, data that does not have any predefined categories, labels, or annotations, such as raw text, images, audio, or video. Unlabeled data is abundant and diverse, and can be obtained from various sources, such as the internet, social media platforms, or proprietary datasets. A foundation model trained on text data can be used to solve problems related to natural language processing, such as question answering, information extraction, etc. The possibilities for what a foundation model can generate are endless and depend on the creativity and ingenuity of the users who apply them to different problems and domains. Large language models utilize a specialized neural network known as the transformer to grasp patterns and relationships within textual data. They undergo pre-training on extensive text datasets and can be fine-tuned for specific tasks. The goal of the language model is, given the preceding words in a context, to predict the next word. While this example pertains to the English language, the prediction could apply to a computer programming language or another language. The model generates text one word at a time based on an input prompt provided by the user. In this case, the input prompt is, "Write a review about an Italian restaurant I visited and enjoyed." The input prompt is broken down into smaller tokens that are then fed back into the model. The model then predicts the next word in the sequence based on the tokens it has received. This process continues until the user stops providing input or the model reaches a predetermined stopping point. LLMs are constructed based on tokens, which represent the smallest units of meaning in a language. Tokens encompass words, characters, subwords, or other symbols representing linguistic elements. The transformer model architecture empowers the LLM to comprehend and recognize relationships and connections between tokens and concepts using a self-attention mechanism. This mechanism assigns a score, commonly referred to as a weight, to a given item or token to determine the relationship. Generative AI models often involve complex mathematical operations and require intensive computations. GPUs are designed to be highly effective for parallel processing. This parallelism enables faster training and inference times for generative AI models compared to using traditional CPUs. GPUs excel in parallel processing, matrix operations, memory capacity, and memory bandwidth, making them an ideal choice for powering up generative AI. They significantly accelerate the training and inference processes, enable working with large-scale models, and support real-time applications. For example, ChatGPT was trained on 10,000 NVIDIA GPUs for weeks. While generative AI offers significant benefits, including increased efficiency and cost savings, its adoption does not come without challenges. To successfully implement such solutions, you'll need to address various technical, ethical, and regulatory issues. It's our responsibility to build using guardrails or rules to mitigate inappropriate outcomes. Data privacy and security. Generative AI use cases in the healthcare and financial sectors should be monitored very closely to forestall any money-related or sensitive data leakages. IP rights and copyright. Generative AI platforms should mitigate copyright infringement of the creator's work. Bias, errors, and limitations. Generative AI is just as prone to biases as humans are because in many ways it is trained on our own biases. Ethical implications. Determining responsibility for the outputs of generative AI can be challenging. If AI systems generate harmful content, it may be unclear who bears responsibility, the developers, the users, or the technology itself. Malevolent activities. There is no state-of-the-art know-how that wrongdoers can't put to their evil uses, and generative AI is not an exception where fraudulent scams of various kinds can be created. Having gained a deeper understanding of generative AI, let's now explore its practical applications in the enterprise. Generative AI is a powerful branch of artificial intelligence that holds immense potential for addressing various challenges faced by enterprises. While many customers have previously explored AI using traditional classification, named entity recognition, or NER, and natural language processing, or NLP tasks, there's a gradual migration towards large language models for these familiar tasks. As organizations become more acquainted with LLMs, they're increasingly recognizing the value of generative AI and expanding its application across various workloads. In this slide, we'll explore key scenarios where generative AI can be leveraged to effectively solve enterprise challenges. Generative AI produces new content based on patterns and trends learned from training data. Traditional AI, on the other hand, focuses on detecting patterns, making decisions, honing analytics, classifying data, and detecting fraud. Generative AI and traditional AI are not mutually exclusive, but complementary. While generative AI presents exciting opportunities for enterprises to overcome challenges and unlock new possibilities, traditional AI models are still able to address many use cases and tend to be less compute-intensive. This chart shows the customization spectrum that different enterprise customers would need based on their generative AI use cases. The largest category on the left pertains to generative AI as a service, likely the one familiar to many through experiences with ChatGPT. Here you input a prompt and receive a corresponding response. If the response is unsatisfactory, you can modify the prompt to obtain a new one. While the model remains constant, it receives input refinement or reinforcement to assist in delivering a more accurate answer. The next level, moderate customization, is where enterprises will add additional parameters to the existing pre-trained model and slightly tune it. This moderate customization still requires infrastructure expertise and investment. The next one is extensive customization. Here's where customers are building their own foundational models. They require extensive fine-tuning and even more investment in infrastructure and AI expertise. Building foundation models from scratch requires a lot of data and compute resources, making it a very costly process. It's often large technology companies, research institutions, and well-funded startups that have the resources and expertise to undertake such projects. Customizing a pre-trained model, on the other hand, requires less data, resources, and expertise. It involves feeding the model with domain-specific data tasks and adjusting the model parameters accordingly. It's less resource-intensive, but also requires some knowledge of the model capabilities, the data format, and the evaluation metrics. As a result, many organizations choose the more cost-effective approach of leveraging existing foundational models, like those offered by AI research companies, and fine-tune them to their specific needs. While generative AI shows tremendous promise for delivering business value, companies must also make substantial investments to build custom LLMs to meet their needs. Building custom LLMs requires massive amounts of training data. To get these models to understand, predict, and generate human-like text, we need to feed them with a substantial corpus of diverse and high-quality data. This presents a challenge in terms of not only data collection, but also its curation, storage, and management. The sheer scale of computations required for training these models is immense. It demands a robust, large-scale computing infrastructure, which is expensive. Implementing LLMs requires more than just the right hardware. It also necessitates the right software. Organizations need tools that address both training and inference challenges, from algorithm development to accelerating inference on a distributed infrastructure. LLMs are complex and sophisticated. They require a deep understanding of AI, machine learning, and data science principles. Building and fine-tuning these models require teams with a high degree of technical expertise in these areas, which can be difficult to find and retain. Embarking on the journey of generative AI involves some key steps. In essence, deploying generative AI in an organization is not just about the technology, but also about aligning it with business goals, team capabilities, data strategies, infrastructure readiness, and a commitment to responsible AI. Identify the business opportunity. We must focus on use cases with substantial business impact and ones that can be enhanced by our unique data. These opportunities form the bedrock of our generative AI strategy. Build out domain and AI teams. This involves identifying our internal resources and coupling them with AI expertise from partners and application providers, forming an interdisciplinary team that understands both our business and the AI landscape. Analyze data for training and customization. This is where we acquire, refine, and protect our data in order to build data-intensive foundation models or customize existing ones. Invest in accelerated infrastructure. This includes assessing our current infrastructure, architecture, and operating model, while carefully considering associated costs and energy consumption. The right infrastructure will enable an efficient and effective deployment of our AI solutions. Develop a plan for responsible AI. This means leveraging tools and best practices to ensure that our AI models and applications uphold ethical standards and operate responsibly. In essence, deploying generative AI in an organization is not just about the technology, but also about aligning it with business goals, team capabilities, data strategies, infrastructure readiness, and a commitment to responsible AI. Let's look at some of the steps involved in building generative AI applications, from data preparation to deploying an LLM into production. The data acquisition phase involves collecting and preparing the data that'll be used to train and fine-tune the LLM. The data can come from various sources, such as public datasets, web scraping, user-generated content, or proprietary data. It's important that the data is diverse and representative of the target domain. Once there's enough data gathered, comes data curation. This phase involves cleaning, filtering, and organizing the data that'll be used to train and fine-tune the LLM. The pre-training phase of an LLM involves exposing the model to a vast corpus of text data to facilitate the learning of language patterns, relationships, and representations. This phase typically incorporates a foundational model as the starting point. Customization allows the adaptation of a generic model to the specific requirements of a given task or domain, thereby improving its accuracy, efficiency, and effectiveness. Model evaluation is the process of assessing the performance and effectiveness of a machine learning model. It involves measuring how well the model has learned from the training data and how accurately it can make predictions on unseen or new data. After a model has been trained on a dataset, it is deployed for inference, where it processes input data and produces output, such as classifications, predictions, or recommendations, depending on the specific task it was trained for. Adding guardrails to an LLM is crucial for fostering responsible AI practices and mitigating the risks associated with the misuse or misinterpretation of the generated text. It helps ensure ethical, safe, and responsible use of the model. The NVIDIA Generative AI platform is built on robust hardware, versatile software, and high-quality enterprise-grade support. This combination allows NVIDIA to provide a fully production-ready generative AI solution to empower enterprises to develop custom large language models for diverse applications, such as language processing, multimodal use cases, healthcare, life sciences, and visual content creation. At the pinnacle of this platform, NVIDIA has developed AI Foundations, a set of tools and services designed to advance enterprise-level generative AI. These tools allow for customization across various use cases, from text-based applications through NVIDIA NeMo, visual content creation with NVIDIA Picasso, and biological computations using NVIDIA BioNeMo. These services are layered atop the NVIDIA AI Enterprise, a software suite that streamlines the development and deployment of generative AI, computer vision, and speech AI, allowing organizations to focus more on extracting valuable insights and less on maintenance and tuning. At the base of this technological pyramid lies NVIDIA's accelerated compute infrastructure, which is flexible and versatile. It can operate anywhere, be it on cloud platforms or on premises. Well done on completing this unit. Now that you've finished this unit, you should be able to explain what generative AI is and how the technology works. Discuss the generative AI market trends and the challenges in this space with your customers. Describe the steps required for enterprises to unlock new opportunities for their business. Welcome to the Accelerating AI Using NVIDIA GPUs unit. This unit introduces you to NVIDIA GPUs, the engines for accelerated compute. Let's jump over to the agenda to see what we have in store in this unit. In this unit, we cover a historical perspective on GPUs, looking at why GPUs were developed in the first place and how they've evolved to become a key component for accelerating computing in the modern data center. A deep dive into general GPU architecture. A head-to-head comparison between CPUs and GPUs. An overview of GPU server systems within the data center. Lastly, an introduction into the last 3 generations of NVIDIA GPU architecture. Let's examine the learning objectives for this unit. After completing this unit, you should be able to recall significant milestones in GPU history and describe key developments in the evolution of GPU technology. Explain the core components of GPU architecture and their functions, demonstrating a clear understanding of how GPUs work. Analyze and compare the architectural differences between CPUs and GPUs, highlighting their strengths and limitations in various computing scenarios. Apply knowledge of GPU server systems to plan, configure, and deploy GPUs effectively, taking hardware configurations and deployment strategies into consideration. Evaluate NVIDIA's AI GPU families, assess their features, and determine which GPU family best suits specific AI and deep learning use cases based on their capabilities and characteristics. We have a lot to cover, so let's get started. Delving into the rich and ever-evolving history of GPUs, we uncover the milestones and technological transformations that have shaped the world of graphics processing. A graphics processing unit, or GPU, is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer intended for output to a display device. Computer graphics have undergone significant evolution since the 1970s. Their importance cannot be overstated, as humans primarily rely on vision to process the information presented by computers. Images on screens are comprised of picture elements, or pixels. A pixel is the smallest unit of a digital image that can be displayed and represented on a digital display device. Pixel characteristics include position, color, and brightness. Every pixel in an image must be processed at such a rate that the human eye does not perceive any delays or inconsistencies as it absorbs the image being presented. As display and computer technology have advanced, screens now have more pixels, leading to more realistic image representation. This is referred to as screen resolution, which represents pixel density. The processing behind the pixels is done by the GPU. As screen resolutions have increased, the processing power necessary to represent each pixel has also increased. GPUs have evolved over time to become a fundamental building block in computer architecture. The 1980s saw the development of individual graphics display processors, and the 1990s sees the development of separate boards or cards that can be modularly replaced in computer systems. Now that you have an understanding of the history and evolution of the GPU, let's turn our attention to this groundbreaking architecture. GPU architecture forms the core foundation of modern graphics processing. In this exploration, we'll delve into the intricate design and functionality that powers these essential components of accelerated computing. This is an image of a typical GPU. At the heart of the chip are thousands of GPU cores. A core is the component of the GPU that processes data. Onboard cache memory, which acts as a typical cache, storing a copy of everything for quick, reliable data access. Parallel processing is possible with the use of multiple cores. Closest to the cores is the high-speed GPU memory. This memory is designed specifically for GPU use and can be shared with other GPUs. Now that you have an understanding of the general GPU architecture, let's turn our attention to the factors that have led to the rise of NVIDIA GPU computing. AI models continue to grow in complexity and at an astonishing rate. In just the past 3 years, the size of state-of-the-art AI models has grown by 3 orders of magnitude, and this exponential pace will continue. This growth in data and AI model sizes requires more compute, which is possible through GPUs but not through CPUs. Also required, a mature set of frameworks and tools to maximize performance and accelerate deployment. NVIDIA is at the center of the AI stack, from architecture and platforms to CUDA, from frameworks to the Triton server and NGC. GPU computing has given the industry a path forward to keep up with the expected performance evolution. This success is achieved through a highly specialized parallel processor design, which permeates the approach to the system design, system software, algorithms, and optimized applications. Continuous optimizations between hardware and software produce ongoing performance gains. Let's explore some key data center trends that also contribute to the rise in GPU computing. The data center landscape is accelerating. Consider the pace at which new services are being adopted, and to see how AI is accelerating the adoption of new services and capabilities. For instance, let's examine the time it took these apps to amass 100 million users. WhatsApp attained 100 million users in 49 months. ChatGPT did so in just 2 months. AI is accelerating how fast new services come along and connect with the community, and this is stimulating demand for advanced computing power. At the same time, there is sensitivity to climate change and the need for greener computing. There's also a challenge to get access to more compute in data centers around the world. Data center energy usage is exceeding 200 terawatts per year. The data center represents about 2% of the global energy usage, and this percentage is projected to increase to 5% by 2030. Data centers are power limited and take years to plan and build. To meet the demand to deliver these new services, data center operators need to optimize the infrastructure they have with the power-constrained data centers they have. Accelerated computing is one way to achieve that goal. Let's explore why accelerated computing is the path forward. NVIDIA CEO Jensen Huang famously stated Moore's Law is dead, making the bold claim several times dating back to 2017. The end of Moore's Law refers to the slowing down of exponential transistor density growth on microchips, leading to challenges in achieving regular and significant performance improvements in traditional semiconductor technology. It's essentially a physics problem, as transistors would eventually reach the limits of miniaturization. To see NVIDIA CEO Jensen Huang discuss this principle, click on the video from his GTC 2023 keynote address. CPUs are simply unable to keep up with the complex workload demands associated with accelerated computing. This limitation will only get worse as the size and complexity of models increase. Accelerated computing requires a comprehensive and integrated full-stack approach that encompasses hardware, software, and frameworks to harness the full potential of accelerators like GPUs for complex workloads. For example, an NVIDIA AI platform with H100 GPUs set new time-to-train records at scale across every workload. This includes the new LLM workload, where training times were reduced from days to hours, and in the case of the largest LLMs, from a month down to a week. It's important to highlight that NVIDIA consistently pushes the boundaries of GPU technology, as demonstrated by our latest innovation, the Grace Hopper GH200, which we'll delve into in Unit 7, which focuses on compute platforms for AI. Let's perform a deep dive comparison between the CPU and GPU to better understand the strengths and weaknesses of each. In the world of computing, understanding the distinctions between CPUs and GPUs is pivotal. In this topic, we embark on a journey to compare and contrast these fundamental processing units. Central Processing Units, or CPUs, are a computer component designed to process complex instruction sets that execute code and manipulate data. Originally, instructions were processed one at a time in the processing unit of the chip, called the core. The core reads and executes the program instructions. As CPU architecture evolved, multi-core processors were developed. This allowed several instructions to be processed simultaneously, leading to an increase in processing performance. GPUs are designed to execute simple instruction sets. Consequently, the number of cores that can be built in a comparatively similar silicon area is much larger than with the CPU. With relatively many more cores than a CPU, a GPU allows processing many simple instructions simultaneously. Both CPUs and GPUs are system components that work in tandem to process code and data. Let's look at some CPU characteristics. Over the last few years, CPUs have moved to a multi-core architecture, with the latest CPUs containing up to 128 cores with fast clock speeds. CPUs also have large main memory. However, the bandwidth of that memory is relatively low, which affects how quickly we can move data about. CPUs are designed to run multiple different applications concurrently. Each of these applications is assigned to a single thread or a small number of threads and is scheduled in a time-sliced manner to run on the CPU. This requires low latency to minimize the delay between issuing a request for data and executing the instructions on the data. This implies large caches to hold the data required by the threads and complex control logic to ensure that the data is ready to go when the thread is running. One consequence of this is that a large amount of the silicon on a CPU is dedicated to data movement, meaning that CPUs have relatively low performance per watt, as a significant proportion of the energy is used for data movement rather than actual calculations. In addition, there are cache misses when trying to access data, which isn't in the cache yet, which can be very detrimental to performance. Let's look at the GPU in comparison. A GPU is optimized for executing highly parallel tasks, stemming from its roots in generating actual computer graphics, where the same operation is applied to millions of pixels multiple times a second in order to render scenes. Modern GPUs have a huge number of compute cores, over 10,000 for some of the latest cards. However, these compute cores don't have the complex logic for prefetching data, for example. So instead, the GPU deals with the issue of latency by hiding it with computation. Essentially, we assign the GPU more tasks than its physical cores can handle, contrasting the approach taken with the CPU. The GPU scheduler launches a thread that tries to execute an operation, for example, an addition. If the data is not ready for the thread to use, it issues a fetch command to the memory, and it stalls while waiting for the data to arrive. The scheduler then moves on to another thread to execute its instructions, and so on and so forth, creating a pipeline of issued instructions across a series of threads. Eventually, the original thread's data is ready and can continue execution. This switching between the threads hides the latency of the memory fetching and the issuing of instructions. Thus, the more work given to the GPU to perform, the easier it is for the scheduler to hide this latency. So what's needed is many overlapping concurrent threads. This contrasts with how we program for the CPU, where we typically allocate 1 or 2 threads per compute core. To support this, the GPUs have a very large register file to hold the state of the threads, and switching between them happens at no time penalty, even as often as every clock cycle. As such, most of the silicon on a GPU is given over to computation rather than data movement, giving them very efficient performance per watt. In addition, a GPU has very high bandwidth main memory compared to a CPU. As many applications are bandwidth bound rather than compute bound, this can deliver significant performance improvements. The additional bandwidth, though, comes at a cost, with the GPU memory being significantly faster but relatively smaller. For example, the H100 GPU has an 80 gigabytes memory version, large for a GPU, but small compared to the CPU. However, it runs at a massive 2 terabytes per second bandwidth, pretty much an order of magnitude faster than the CPU memory. Let's dive deeper and explore how GPU acceleration works. A typical application has parts which need to be executed sequentially, and parts which can be executed in parallel. Although the parallel parts may only be a small part of the overall application, they're usually the most compute-intensive and time-consuming. Therefore, by executing them in parallel on a GPU, we can see huge increases in performance, often orders of magnitude faster than on a CPU alone. There are many algorithms used across a huge range of domains which can be parallelized, and thus see significant performance improvements from this approach. let's contrast how data is processed by a CPU and GPU. Let's consider how the flow of data occurs for those tasks that are offloaded between the CPU and GPU. Note that the CPU and GPU are two distinct entities. They each have their own memory. So we need to bear this in mind when programming for the GPU. First, we need to move the data we wish to work on from the CPU memory to the GPU memory. This is usually via the data path provided by the Peripheral Component Interconnect, or PCI, bus. The code to be executed by the GPU on the data is then copied from the CPU to the GPU. Once loaded, it is launched and the operations on the data take place. Within the GPU, the data takes advantage of the various layers of cache for faster performance. After the GPU finishes processing, the resultant data is copied back to the CPU memory for any additional processing if required. Although this basic processing flow illustrates data passing through a PCIe bus, it's important to mention that alternative GPU interconnection methods like NVLink exist. We will delve into these in a subsequent unit. Now that you have an understanding of the way data is processed from both a GPU and CPU perspective, let's turn our attention to GPU server systems. GPU server systems represent the backbone of high-performance computing and deep learning infrastructure. In this section, we'll navigate the fundamentals of GPU servers and their ever-growing ecosystem. A GPU server is a specialized computer system equipped with graphics processing units, or GPUs, designed to accelerate complex computations in the following ways. GPUs excel in parallel processing tasks, making them ideal for tasks such as deep learning, scientific simulations, and data analysis. GPUs contain thousands of cores that can perform multiple calculations simultaneously. This parallel processing capability enables faster execution of tasks compared to traditional central processing units, or CPUs, especially for applications that involve massive data sets and complex algorithms. GPU servers are optimized for specific workloads, such as artificial intelligence, machine learning, and graphics rendering. They can dramatically reduce processing times, enabling researchers, engineers, and developers to solve complex problems and innovate more efficiently. NVIDIA offers specialized GPUs designed for data center environments. While typically available in a PCIe form factor, GPUs can also come in an SXM or MXM form factor. Flagship examples of types of GPU systems include DGX H100 is a fully integrated hardware and software solution on which to build your AI center of excellence. NVIDIA HGX H100 combines H100 Tensor Core GPUs with high-speed interconnects to form the world's most powerful servers. The NVIDIA H100 PCIe debuts the world's highest PCIe card memory bandwidth, greater than 2,000 gigabytes per second, GBps. This speeds time to solution for the largest models and most massive datasets. NVIDIA MGX, a modular reference design that can be used for a wide variety of use cases, from remote visualization to supercomputing at the edge. MGX provides a new standard for modular server design by improving ROI and reducing time to market. NVIDIA cannot do it alone. Therefore, we tap into a robust partner and cloud service provider ecosystem to power their accelerated compute solutions. In today's enterprise market, modern data centers are responsible for almost any computing challenge. With AI, high-performance computing, and data science growing exponentially, there is no doubt that an enterprise data center will need to have GPU systems to support this demand. All major data center server vendors offer GPU-based AI systems: NVIDIA, Cisco, Dell, HPE, IBM, Lenovo, and others. These servers support 2 to 16 GPUs each and can be interconnected to create multi-server parallel processing systems. Also, NVIDIA GPUs have been adopted by every major cloud provider, extending accelerated computing into the cloud. Let's explore how GPUs are consumed within the data center. There is an ever-expanding range of workloads that lend themselves to GPU acceleration. Compute-intensive tasks like AI training and inference, data analytics, and high-performance computing, or HPC. general-purpose tasks like visualization, rendering, virtual workstation, and deep learning. High-density virtualization through solutions like virtual desktop and workstation. Enterprise edge solutions in controlled environments. Industrial edge solutions within industrial or rugged environments. Desktop workstations that support design, content creation, and data science workloads. Mobile workstations that facilitate design, content creation, data science, and software development workloads. Now that you have a solid grasp of the primary applications of GPUs in the data center, let's review the key takeaways from this unit and look ahead to the next lesson in the course. Now that you've completed this unit, you should be able to recall significant milestones in GPU history and describe key developments in the evolution of GPU technology. Explain the core components of GPU architecture and their functions, demonstrating a clear understanding of how GPUs work. Analyze and compare the architectural differences between CPUs and GPUs, highlighting their strengths and limitations in various computing scenarios. Apply knowledge of GPU server systems to plan, configure, and deploy GPUs effectively, considering hardware configurations and deployment strategies. Evaluate NVIDIA's AI GPU families, assess their features, and determine which GPU family best suits specific AI and deep learning use cases based on their capabilities and characteristics.